Today is kind of like cleanup on aisle 5. We're gonna just wrap up very quick stuff on the binary trees, and then try to introduce the more formal language for asymptotic analysis, which is something we've been talking about pretty much the whole semester so far in terms of worst case, best case, but it's the more formal language. So we'll introduce that, show you some code snippets, and that should get us kind of wrapped up relatively early today, which is kind of a nice wrap up or end to the first half of the semester. Quick reminders in case you didn't get this before. So we'll have a midterm practice by noon on Saturday. So heads up for that. I'll probably push an announcement out so you see that. It'll give you a really good sense of what the midterm is going to look like. We'll do a review on Tuesday. I think I mentioned it before. It's kind of optional if you've got other higher pressure things to do or just to study for your midterm if you're off campus rather than just kind of coming in for that. I'll certainly post a video for that. But anybody who comes in will go through the stuff that we've covered. We'll answer questions, the usual stuff. And then our midterm in class, and that will be from 5:10, our usual start time, all the way till 8 o'clock. So that's our 170 minutes total. And I think that should be enough for everybody. It's a little exhausting, so try to come in rested if you can. And don't forget about your homework 4 that's out there. It's kind of a choose your own adventure thing. So once you kind of get past the midterm, you might just want to take a look at that, maybe pick one of those and start maybe just thinking about it. It's not a lot of time to do these things, but if you leave them go till the end, it's kind of a bit of a rush. One of the advantages of maybe waiting a little bit is you might learn some new techniques. So looking at one and thinking about it, or maybe asking me like, hey, what are some interesting approaches? I can give you some hints. And then you kind of keep it as a background thought process, how you're going to solve that thing as we go through the rest of the semester. So, but don't forget about it because you'll come up short on one of your homework assignments. And I'll remind you as usual. So the midterm, again, open book, lectures 1 to 14, including today, quiz 4 ungraded. Don't forget about that one. It's a good practice one, even though it's ungraded. And you can go back and take your extra quiz tries if you have some left over. It won't change your grade for that quiz already. I have to reset your grade to your on-time quiz grade, but it's a great way to practice for the midterm and see some answers that maybe you hadn't seen before. So if you've got unused tries and you want to go back and use them, you're welcome to do that. Okay. And then the Quizlets, of course, hopefully that's helpful in our review. And that'll be it. We'll be here to kind of knock this out on Thursday and then kind of move on. So if you have any questions, I will be around all next week. I'll do our normal office hours before class in my office on Tuesday. So please feel free to stop by. Or if you are struggling with a particular concept, just reach out to me an email and we can set up a quick Zoom or a one-on-one on campus in my office or down here if we can find a common time to go over stuff. Okay. Questions before we push on from there? Yes.
Breakdown or multiple choice versus reading or default.
So you'll get a really clear sense of that with the practice exam, but it'll probably be pretty representative of the quizzes so far. So I think you'll see, effectively an essay question, per se, in line with what you've seen in the quizzes. And many, many of them are going to be probably fill in the blank, I would think. Actually, I take that back. It's really going to be whatever you've been seeing in quiz 1 through quiz 4, because those are really the questions I'm drawing from. So I'll try to if I get that practice quiz out early. Sometimes I get it out as early as, or the practice exam out as early as noon tomorrow, but I'll send a note to everybody so you get a little more time on that, and that'll make things a little bit clearer. Okay. Now, just help me out on this. Every once in a while, we have some internet server issues. So if you are not seeing a picture with a question like this from quiz 3 or quiz 4, let me know. Sometimes Canvas does not post the picture right away, and I haven't quite figured out when and why. But give me a heads up, and it will help me kind of anticipate problems we may have during the midterm. And especially if you take the practice midterm and you're not seeing these pictures, that's a clear sign that something's amiss. So I've been trying to debug this problem for a couple of years now, and I just always want to give everybody a heads up for that. Um, so objectives today, very brief review. We'll finish our AVL balanced binary tree algorithm. There were just two little bits that we'll kind of go through on this. And I always like to point this out actually, that the idea of a family tree from your personal perspective is actually just a binary tree kind of turned upside down, right? So there are so many interesting problems we could solve sort of from a tree traversal standpoint, like our two nodes, relatives, and what's their common ancestor, etc. But really, if we think about our, great grandparents biologically and great great grandparents, it's a power of two kind of thing. If you go back 7 generations, it's going to be 2 to the 7th power, right? So, and back and back and back. If you could, literally go that far back, you'd know exactly how many ancestors you have at that level, which is a pretty fascinating kind of. Oh yeah, we are the results of the binary tree, which is kind of fascinating. So we'll look at our rotations and our for that what we call combo rotations, and then just formally introduce our loop analysis. Talk about big O notation and also what's called big theta notation and big omega notation. So those things are really the kind of questions you get in interviews, and they're the kind of things you're expected to pick up from a class like this. Okay. And we'll use an airplane analogy to help explain that for folks who may still be a little fuzzy on it. So if you remember last time we talked, we introduced this idea of a maximum depth, which we use to calculate our balance factor. And we had to sort of know that at every node so we could figure out the balance factor at the node above that. So we were just sort of calculating the maximum depth and then calculating the balance factor as the right side minus the left. And that really gave us the metrics we needed to perform these rotations. So, and usually you store that stuff at the nodes, even though it costs you a little bit of space, right, to have an integer stored at that node, then, or maybe a character even, or an 8-bit integer. It's good information to have because we can do local fix up without recursively going all the way to the bottom of the tree and recalculating that every single time. Okay. So we need everything to be balanced according to that algorithm, but we don't break the balance at the whole tree when we insert. We just break it at one point, and then we can fix that up. Okay. So we said that's just going to be the difference between the left max depth and the right, and we want to keep that for AVL trees in the -1, 0, and 1 range. Okay. And then just repeat that. And here was our animation. When we rotate to the right, or what's called clockwise, and I tend to say we're rotating around, and I identify the route at which we're rotating around. It's like a teeter-totter. We're pulling up the A and pushing down the B, but I would call that a rotate right around the B, and then a rotate left around the A, which is the root. Okay. So hopefully that's clear, but when in doubt, we'll have a picture like this or an animation on your quiz to help clarify what we're talking about there. Okay. And those are pretty standard rotations, right and left rotational fixes. So we looked at a couple examples. We just said, hey, figure out the height and the balance, figure out where the imbalance is, and then do either the rotate right or the rotate left. And everything else will kind of get fixed regardless of how deep they are in the tree, and nothing above us will actually be changed. So we're really just doing a local fix up and making a relative change. So if we have a 4 depth here and a 1 depth after the rotation, we got a 2 and a 2. Okay. So we sort of need to be able to assess, hey, what needs to be done over here to fix that thing? What kind of rotation? And that's really all we're expecting from you on the quiz and on the midterm. Okay. So no one's going to memorize all that rotation code that we would need to get that to actually work. Okay. So that's our right rotation. And then we had our left rotation as well, which sort of pulls stuff up from the left side and shortens it on the left and balances on the left and right. Okay. Now, those are the simpler cases. We're going to look today at a situation where we actually need to rotate into a combination of rotations to fix the problem. And so that's really where we've come to the full implementation of this AVL tree. Okay. So there's a lot of different kind of balanced binary trees today, that you can choose from, and AVL is just one of them. And they have their own particular algorithm for balancing. But there are 2-3 trees, AA trees, scapegoat trees, they go on and on. Okay, so we're just picking one of them. And as an optional choose your own adventure on Lab 14, you can just have a conversation with Chat GPT. We'll show you that at the end. And it's kind of fun if you've never done this to sort of to sort of explore, different things that we haven't talked about in class. So I find that interesting, but since it's, a little bit out of the standard kind of thing we ask you to do, I will give you another option, which is analyzing some code. So we'll look at that in the lab time. Okay, so moving on. Remember that we got to maintain this invariant or the balance invariant at every node. So we talked about that last time. This is, a hallmark of the AVL tree specifically. So nothing really new there. But let's look at the information that we're storing again, the value, the balance factor, and the depth, and the pointers to the left and right children. That's kind of our fundamental node information that we need to carry around with us. And then the full set of rotational fixes is going to be either what we call the left heavy. So that's a simple rotation to the right. Okay. Or a simple rotation to the left. And then two other cases which require a combo fix. This is the left-right heavy. I'll show you that here in a second. And a right-left heavy. So that in each of those cases, it's going to be a rotation of one direction followed by a rotation on the other side. And I think this is a minor typo here. These two should be swapped, the left and the right here. So let me just make myself a reminder to come back and fix that. But I'll show you this here in the slides that are coming up. So those were the ones we talked about last time. We're going to talk about these two here today, and that should round out things pretty nicely. So there's our left heavy. So we've kind of got kind of a long chain all along the outside of the left, and we said a simple rotation brings that into alignment. So we've kind of seen that before. Okay, pulling up the 7, pushing down the 9, handing across the 8 to the other side. Okay, and here is the rotate from right heavy, rotating to the right. Okay, so we just saw that a moment ago. Nothing new there. 7 comes across, or sorry, 7 doesn't come across. The 4 comes across to the other side. Okay, this is the new one. So this is not solvable with a simple single rotation. What we need to do here, once we recognize this particular case, is rotate at the 2. So left rotate around the 2 to pull up the 4 and the 5, handing the 3 across. Okay. And then we do a rotation right at the top to pull and shorten that far outside. So that's our standard left heavy situation. Okay. And now we bring ourselves into balance. Okay. So it's kind of all about, in terms of the quiz questions, recognizing, is this the longest chain or is this the longest chain, right? So if you got something like this, you got to do a rotation to pull that up, fix that locally, right? Fix this tree. Then you can kind of go back up here and pull up this tree to fix that and get back to balance, okay? So that's our kind of left-right heavy or case 3 situation. And of course, there's one for the other side too, right? The longest chain kind of is a mixture. So we're going to rotate right around the 6 to pull up and fix that subtree. And then we'll rotate left around the 2 to pull up and fix that other side there, the right heavy. Okay. And that's it. Those 4 cases, just sort of recognizing those And then, of course, doing the pointer fix up to actually fix that is all we're really looking for in terms of your kind of your understanding from this class, right? We're not going to go too much deeper than that. Doing that in code, of course, requires, good bit more, good bit more work to do in code. So we're not going to really take you there for this particular course. Okay. Questions about the combo rotations, though, before we kind of push on with those. Okay, a little Quizlet time helps for sure. Of course, the practice quiz for homework for quiz 4 is also going to help you on that. So heads up for that. Let's just take a look, I guess, at a few before we get to our asymptotic stuff. So here, the longest one is to the outside, not on the inside, right? So here we're going to end up doing a standard rotation. That's our left heavy. Okay, so we're going to rotate around the 6 and pull up the 2. So that's one. If that causes you a little head scratching, you might want to think about, what would happen if we tried a different one, right? If we try to pull up the 7, of course, we're just making this longer, etc. So you can play that out in your mind, or have some paper and some pencil, which is a good idea for the midterm for this kind of stuff. So you might want to think about bringing something to class for that. But that's going to be our fix, standard left heavy, okay, or left heavy fix. Okay. Let's take a look at another one. So this one's a little bit non-standard. This is a combo rotation. So we're going to be pulling up around the 3. So left rotation around the 3, right? And that's going to then require a right rotation around the 8. Okay, so that's going to pull us back up into balance. Okay, and this one, of course, is right rotation around the 7 to bring up the 5, followed by a left rotation around the 3 to get us back to balance. Okay. So there'll be a few of those, and those are kind of a little bit more obvious because they're fuller branches. You're going to have some situations where the branches are not very full, okay? But this is basically all of the things you need to know about the AVL tree, right? If you had to answer some questions, they're all kind of thrown together on this page. I won't take you through them all again. Different kinds of trees will use different kinds of binary search trees will use different kind of balancing factors, different ways of tagging when something is out of balance, and sort of a different strategy about how long they wait before they might actually bring something back into balance. So these things are somewhat exotic, and people have made up a variety of different ones. These are just the most popular ones out there. And this one's the oldest one out there. Okay. So there are your kind of Quizlet links, or just go to the overall Quizlet study slides if you like. I think you can find those links in a couple of our lectures so far. And that should cover all of the key stuff for binary search trees that you need to know. Okay. Okay, so let's go back to describing growth and kind of officially introduce our language for the rest of the semester. So we've been talking about putting in counting of copies, counting of swaps. That's what I would call empirical growth. It's like we're kind of measuring something very directly, printing it out, and then trying to have some intuition based on the numbers that we're printing out. Okay, and that growth is almost always with respect to n. As n gets bigger, what happens to something that we're trying to measure? Okay. So we've introduced this wording where we say it's going to be constant, which means, okay, let's say it takes 5 seconds to sort 1,000,000 things, and then it takes 5 seconds to sort 100 million things. Well, that's constant, okay? Even if it takes 10 minutes in both of those cases, that's constant, right? We have some overhead, we pay for it, but it's not going to grow, okay? So we've talked a bit about these. Logarithmic is any base. It doesn't have to be base 2. It could be base E or base 3. It really depends on the algorithm itself. Okay. Linear arithmetic, is n times the log curve. So it's just n log n, again, for some base. It could be any base, quadratic, cubic, and exponent we haven't done too much discussion on, but it's easy to accidentally screw up your code so you have something exponential, or to write some code that gets you the right answer, but does so in a very exponential way. If we get time to talk about dynamic programming actually comes into its own when we have algorithms that, like, at first glance are exponential. We might think, okay, well, we can't do it any faster. But it turns out with dynamic programming, we can store some information along the way and reduce that cost to maybe something like quadratic or even linear. So we'll try to get you into some dynamic programming before the end of the semester, because that is kind of a cool little area of coding that you probably will end up running into at some point in your life. So if you keep coding, okay. But those are our curves we talked about before, and just to kind of peek at them one last time here, you can pull these up. But there you kind of go, and you can see that the quadratic ones, as n gets bigger, they get pretty ugly pretty fast. So we really want to be over here in the logarithmic area if we can. And even the linear rhythmic, which is n log n, we can kind of see over here, that black one is actually, it might seem kind of steep, but it's really not as steep as some of these other ones over here, right? So that's our n log n, okay? So still not terrible, right? That's our linear rhythmic performance curve, okay? Compared to the quadratic and the exponential, okay? And there are lots of names for all of these other ones. We're not going to really go there, but if you ever like to do stuff like computational geometry or drawing curves, you can do all sorts of polynomial curves and get into all this stuff, which is pretty cool stuff. Okay. So here's a couple graph pictures just to remind you one last time. Again, if it takes 10 seconds, no matter what the value of n is, that's pretty much constant, right? If it is a straight line on a linear graph axis, that of course is linear, right? Even though the slope can be steep, it's still growing in a linear way, okay? So just because it's steep does not mean it's not linear. Linear means we're increasing by a known amount for every increase of n. That's going to be a constant slope across there, okay? And there's just a couple examples, right? F of n equals x or f of n equals 5x, both linear, okay? So that's not going to really change our assessment in a broad way. Quadratic, let me get rid of my stuff here up top. So quadratic, the trick for this is anytime we double n, we get a 4x growth on whatever it is we're measuring, okay? So you can kind of think of it, even though my graph scales are a little off here, if I am going from 50 to 100, I'm going to get a 4x growth. So 2,500 for my, let's say, number of swaps going to 10,000. That's a 4x growth for a doubling of my n. And that's classic quadratic. And that's kind of something we try to get at on our first homework, okay? So if that thing grows consistently in that way, you're pretty much looking at a quadratic performing algorithm. So you really only need to test 2 or 3 sample points to kind of come up with the answer for that if you really want to do that. Just grab your n, double it again, check to see if it's quadratic or not, and at least you can eliminate quadratic as a possibility, okay? Obviously, if you graph the curve, it's a little more helpful, but you don't even really need to do that to know, okay? And remember that we can still have quadratic, right? And it can be scaled by some factor. Here you can kind of see our cubic difference, x to the third versus x to the second. That really should say n instead of x, but that's our horizontal axis, and growing that. So if you're looking at a scaled graph, it can be a little confusing to tell the difference between a quadratic and a cubic, right? So you kind of have to do the sampling and check the values on the graph to really know, okay? But in this particular case, right, if we were to sort of triple n, right, So we go from a, what did we say, a 23 to a 70. Oh, so f of 70 is going to be 343. We're sort of seeing cubic growth in that. Okay, so you just got to plug and chug a few numbers. And instead of doubling, you actually want to triple that. So we had a 23, and I think we tripled that to get to 70. I'm not quite sure how I came up with 70 on that one. But I think that was our closest number I had data for. Okay, but I think you kind of get the idea there, right? Tripling of the value instead of doubling, and that should give you a tripling of the result as well. Okay, or sorry, each time we triple n, we have a cubic performance or cubic change at some scale c. Okay. Okay, so I won't see too many of those. This is our log base 2 performance. So in this one, for each time we double n, we have a constant growth. So in this case, the doubling of n from 4 to 8 will actually grow by a constant amount. In this case, 1, right? We go from 2 to 3 to 4. That's a classic logarithmic growth. Okay. And then there's our linear rhythmic. And for this one, you'll just have to sort of plug and chug to see if you're actually getting a linear rhythmic result on that. Okay. Okay, so asymptotic analysis. So what is this all about? So those are the kind of behaviors we've seen. In terms of the notation, when we talk about the upper bound or the worst case, we officially refer to that as big O notation. So it's usually written in a capital O with parentheses with the thing that indicates whether we're linear. So we would say big O linear or big O n in terms of the notation, and that tells you that's going to be a linear performance or linear worst case for that particular algorithm. Big O n log n, or what would be described as big O linear rhythmic, is just saying that's our worst case. Big O of 1 or a C means a big O constant, so we're not going to ever see that thing grow with regards to n. Okay, so that is the most common phrase that gets thrown around in algorithmic assessment. But sometimes people get it wrong. They'll say, oh, I'll say, what's the best case? And they'll say, oh, it's big O linear. And I'll say, no, big O is not best case. Big O is worst case or upper bound. It's like what's the worst day you're ever going to have? Okay, so if your boss says, when are you going to have that done? You would say, in the worst case, I'll have that in a week. You might get it sooner, but your worst case is bounded by that 1 week estimate. Okay. Now, when we talk about, let's say you get really good as a software engineer at saying how long it's going to take you to fix a bug. And you could say, I'm going to fix that in a week, give or take a day. We would tend to refer to that as a big theta assessment. Big theta occurs when your upper and lower bounds are very tight around your assertion. Okay. So it's not like you could potentially be quadratic, but but in your best case, you'll be linear, right? It's like, no, you're going to always be kind of n log n, for example. And merge sort was one of our algorithms we saw that does that. Okay. So a merge sort has an upper and lower bound that's n log n. And then the other one is big omega, which does not get talked about that much. But if we say, what's our best case on a particular algorithm, that's big omega. Okay. So it's a little difficult to type that on a keyboard using the omega symbol, which is probably why so many people incorrectly use the big O when they're really talking about lower bound. But correctly, you would say it's a big omega if we're being asked about its lower bound. And lower bound means what's the best situation? What's our best case scenario? Okay. My best case scenario is I'll find it in an hour, but I'm not going to find it any faster than that. Okay. So that's what we would call big omega. Okay. So that's really as far as algorithmic analysis tends to go in terms of the symbolism, but it seems very kind of unclear sometimes, and people do tend to use it incorrectly. But I think this is the proper way you would actually refer to those things: upper, lower, and tightly bound in the middle. Big theta notation. Okay. So hopefully not too mysterious. And you can kind of look all of this stuff up, and it derives from mathematics. So it goes pretty deep if you want to go deeper, but that's generally what we hear talked about in terms of algorithmic discussions. Okay. Oh, thank you. Okay, I'll leave you there. You can also jump into Comic Con Academy if you want to check a little deeper on that as well. I'll just do this plane analogy here, since sometimes, this is helpful too. If we have plane A climbing as fast as it possibly can, and plane B is climbing somewhat erratically at the beginning, but more or less stabilizes somewhere underneath our maximum climbing rate, that's going to be considered to be worst case whatever this plane is, right? So we're basically staying underneath some upper bound after some point P where things stabilize, okay? So we would try to find a description of the upper bounding plane, even though our algorithm might wobble around underneath it somewhere. Okay, so we tend to do better than our worst case a lot of the time is really what that comes down to, okay? So whatever we would use to describe plane A is probably the upper bound for our algorithm. Okay. And then our big omega, just the opposite, of course, right? So what is the slowest descent the plane can possibly take off? And maybe, our plane B is gonna somewhere wobble around that neighborhood. But after some point P, where N gets really big, that's really where the analysis kind of stabilizes. So the point of these graphs are, don't worry about what's happening in here until N gets pretty big. That's really kind of the area where we're talking about, beyond some initial point P where things start to average out, okay, in terms of the overhead. Okay, and then the tightly bound is if more or less the upper and lower bound is coming from the same equation, linear arithmetic times 4 instead versus linear arithmetic times 3, then we would say that's a pretty tightly bound algorithm. And that's where we would describe that as big theta constant or big theta linear arithmetic. Okay. So that's really all there is to that terminology. Hopefully feels somewhat aligned with what we've talked about so far. Now, the only thing that's not really represented here is average performance. So we haven't really talked about average performance with asymptotic symbolism. And that's also a point of confusion. It was for me too, when I first started, trying to understand how people intended this language to be used. I kept hearing questions or reading questions. Okay, and what's the average performance? But there isn't really a symbol for average performance. It is often confused with big theta, but big theta is not about average performance. It's about a performance that is falling very tightly within an upper and a lower bound. They seem closely related, but they are indeed two different things. Because as we've seen, we could have a really poor sorting algorithm, where we have got to sort something in reverse order, but I could have a really good scenario where I'm sorting something that is already in order, but the average performance is going to be somewhere in the middle. So it is not the case that a big theta means the average performance. There really are two separate things, okay, and somewhat easy to confuse. Merge sort is our one clear example we looked at that is tightly bound. It has an upper and a lower bound that are essentially n log n. Okay. So really, if we were going to dig into it more, we'd get into a lot more of the math. And in your more advanced algorithms classes, which we are not really trying to tackle here, there's something called recurrence relations that is fundamentally a mathematical assessment of recursive code. So you may be interested in recurrence relations. And if you go on to more advanced algorithms classes, you will very likely be asked to write and develop recurrence relations. But those are fundamentally mathematical operations around the code that and the structure of the code that you're seeing. So we're not going to dig into that stuff here. We're mostly just introducing the correlation between our empirical results and this kind of more formal notation. So let's see if we can look at some code. There's terminology here. You can kind of look at the Quizlets and test yourself on this stuff, just so you get yourself familiar with its more casual meaning. But let's take a look at some loops and make sure we can all kind of see the correlation with this terminology. So if I have a loop like this, for I equals 1 less than some small constant value c, and I do something, right, inside of that loop, n is not part of that equation. So a loop like this isn't going to, grow with n. It's going to be constant, right? So it's probably a little simplistic, but a piece of code like this not going to be growing based on n. So we're independent of n, I guess is the best way to say it. So we would say that's a constant piece of code, right? Linear time would be more like this, right? For I equals 1 less than n, I equals I plus c. So even though we're skipping I values, right, we're still going to grow based on n. So if n gets bigger, our computation time gets bigger, okay? So inside of here, we might have some constant expressions, but the outer loop here is going to be the worst case situation. So we're growing with n. So we'd say that that is a linear time worst case scenario, even though it's jumping by some constant factor we don't know about. Okay. Quadratic, of course, two loops inside of each other. Okay, even if those loops are sort of, not perfectly square, right? I equals I plus c, again, skipping by some constant value. We're still quadratic with regard to n in that situation. So double loops, quadratic, pretty straightforward to kind of see that. Three loops, okay, cubic. And you can kind of see where that goes. If you had to explore an n-dimensional space, maybe I should say a p-dimensional space with p nested inner loops, well, that tells you pretty quickly, that you're quintic or, beyond. That's the degree of your polynomial. And that's very, very expensive stuff, okay? So we generally try to avoid that. Function calls that are exponential, right? Where some constant is raised to the power of n. So that is, definitely it's going to kill your computer if you try to do that. So here's an example of an exponential way of calculating the Fibonacci sequence. So I can split left and right, and I will get the right answer, but it's essentially going to mushroom out, creating a branch of 2 at each new recursive level. And that is essentially going to be n 2 raised to the power of n. So in that case, our c is going to be 2, and it's going to be what we would consider to be exponential, which is quite a bit slower than quadratic. And then a couple others. So logarithmic is going to be, we're approaching n, but notice that we're jumping further each time. I equals I times c. So if c was a 2, then we are jumping further and further toward n by a factor of 2 each time. And that, although you might not recognize it at first, is essentially going to be logarithmic because it's a divide and conquer. So we're sort of moving toward our ultimate goal by doubling each time. So we're getting there faster and faster. Okay. So that is one way we might actually see a logarithmic piece of code. Okay. And you could put instrumentation inside that loop to convince yourself of that. As n grows, you're going to have logarithmic base. Okay. So that's our base 2, right? Where our c for growth is 2. Okay, but that could be a 3, and we'd be log 3, or that could be I equals I times 4, it would be log base 4. Okay. Now, let's take a look at this one here, right? So here, sorry, I kind of jumped the gun on that, but that's going to be a log base 5. Okay. Now, most of our divide and conquer algorithms that are recursive, we're dividing in half. Okay, so that is a different way of achieving our logarithmic behavior. Okay, so this is just showing you it in a basic iterative loop. So just kind of in closing, we have our notation, which you should become familiar with, right? Because this is pretty much how people tend to think about things. And this is all worst case assessment. What's the worst it could be? Log n and log n, etc. Okay? And normally the base is not even really included in the conversation, although we've added it for clarity in a lot of our algorithms. Okay? And this is our big O worst case. Okay. And that's kind of it for today. So I just want to make sure we have that terminology before we go into the midterm. And then for lab 14, you got two choices. One of them was designed to be like an easy, lightweight way to learn a little bit more about binary search trees. So there are a number of them out there. And one of my thoughts was, why don't I just let you have a conversation with ChatGPT about it? It's kind of an interesting experiment to see if it's a learning thing or an annoying thing. So if you go to Canvas, and I don't think this is the proper link here, so you'll have to go to Canvas and do it that way, I think. And you're going to have to feed it a specific prompt if you try to do this. So it's in Canvas. The idea is go to a ChatGPT account, presumably yours. You're going to have this is going to be an anonymous share. So you're going to start out your prompt with this. Like this is an engineered prompt. And it's pretty fun to do this if you've never done this. You're going to give ChatGPT as your instructor the rules that you have to follow, right? It's going to ask you 5 questions and you have to ask it 5 questions and it'll tell you when you're done, right? So it's sort of a structured conversation. And when you say goodbye, it'll give you a summary or you can ask it for summary. So basically, this has been tested out a few times and it's relatively well behaved. And when you are ready, just share an anonymous link from your ChatGPT. Okay. Or if you have a similar functionality from Copilot or another AI package that you're using. So, and this is optional. You can take this path or not take this path. You might find it fun. But I've found surprisingly conversation with ChatGPT to be pretty illuminating. But you always, of course, got to check your results. But ChatGPT knows about, of course, all algorithms. So if you want to have an open-ended conversation, it's a pretty illuminating thing most of the time, right? So that's kind of option 1. Don't forget about your loop analysis. And did I miss option 2? So let me see if I can get over to Canvas and show you option 2. I really thought I uploaded this one, but let me go to our view a student, go to our assignments. And by the way, I don't know if you guys know, you can show by date or show by type. I always find show by type with my classes to be a little easier because it just sort of groups things. So it's like, okay, we're on lecture 14. So, where's that? So choose your own adventure, trees or analysis. So that's our ChatGPT conversation. Or down here at option B is just, hey, tell me what the big O and big theta performance is of, this should be big omega, I'll fix that, of this particular piece of code. So it's a little bit gnarly, but you can instrument it fairly quickly if you're interested. See if you can figure out what the big O and big omega, right? Big omega and big O. So this is worst case, best case performance is of this algorithm, okay? So I'm going to be pretty flexible on the grading on this. I'd just like to see everybody take a crack at it. And you could take a guess without instrumenting your code, but it's kind of tricky code. So if you can read it clear enough, you might be able to tell what it's doing. But you may just need to throw a few print statements in there or add a few counter variables. Basically try to assess how many times your sort of making an assignment, right, between two of the, the values, like shifting something in an array. It looks very similar maybe to an insertion sort or something like that. That might be doing a divide and conquer. So, take your best shot at that. I'd just be curious to have everybody think about, what's that thing doing in a worst case scenario. Okay. And then my takeaway here, of course, is I'd like for you to understand which one is which, big omega versus big O. So you'll probably have to just go back and take a look at the terminology from our lecture today. But otherwise, it's really just going to sort the data. It's not even going to print out the values. So you don't need to worry about what values are printed out. You can sort of just kind of assess its execution cost without worrying about that at all. Okay. So those are our two options on the lab today. Any questions on either one of them? Take us back there. Okay, for submission on these, just if you're going to do the chat GPT conversation, just do an anonymous share and submit that link in Canvas. I will not be sharing that with anybody else. Of course, that's your homework, but it won't have any information about your account. So anonymous shares do not have any link back to you or to your account. They're just URLs. Unless you put some personal information in it, it's not going to know who you are. And I won't know that either. So I'll just see the conversation. If you do the other one, if you do the analysis of the code, just submit your two answers, big omega and big O, worst case, best case, and I'll just take that. And you can optionally submit the link with that as well.
You want us to describe lines, like whatever complexity?
Yeah. Well, I'd like to know, do you think it's, linearithmic? Do you think it's quadratic? And, give me some, if you could take a guess at it, and if you don't give me some rationale and you're wrong, I won't give you any extra credit for that. But if you have some explanation and you're wrong, I can at least give you some partial credit on that. So yeah, do your best to explain why you think so. And if you just instrumented the code and you're looking at the numbers and it's like, oh, I can see clearly it's, going through the loops this many times as I double the size of n, that's telling me, blah, that's good enough for me as well, right? So, but in that case, I'd like to see your code link submitted as well, so I can tell. Yeah. So, both of these are a little bit of an experiment for me. So like I said, I'll be pretty lenient on grading on these. I just kind of want to pull us a little bit deeper into one of these directions for some more critical thought. Okay. And with that, we'll just call it a wrap, and I'll stay in case anybody still has any homework questions or any lab questions. But otherwise, I'll see you all on Tuesday for our review, and heads up for announcements. And I'll get all your grades updated by this weekend for sure. So thanks, everybody. I'll see you guys on Tuesday. Get this guy out of here so we can see. Thank you. Thank you. Have a good weekend.